So now you are in Andhra, sir?
No, no, I couldn't go there also.
Oh,
I did it online only.
online only. Okay, okay,
Yeah. So I'm in Math
okay,
Science Institute of Mathematics in Chennai.
okay, okay.
Yeah.
Sir, actually, sorry to actually, the time is 4:30, na? So we have to wait 5 minutes
Yeah,
means.
no, no problem, no problem. No.
Okay, okay,
I came early, that's all.
okay.
No
Sir,
problem.
the slides you will share, sir.
Yeah, yeah, yeah. Should I?
Okay, okay. No, sir. First,
Yeah.
beginning
After.
after that.
Yeah,
Yeah.
after.
Okay, sir. Shall I start, sir?
Yeah.
Okay, sir. So, very good afternoon, everyone. It's my privilege to welcome you all to this special celebration of National Mathematics Day. A day is dedicated to the legendary Indian mathematician Srinivasa Ramanujan, whose contribution to the field of mathematics continue to inspire countless minds worldwide. So to start this program on an auspicious note, let us first invite our head of the department, Dr. G. Ravikiran sir, to extend a warm welcome to our esteemed speaker, Professor R. Thangadurai sir, and all the participants. So please, sir, HOD sir, it's now over to you.
Okay. Thank you very much, sir. Good afternoon, everyone. Good afternoon, Thangadurai, sir.
Yes.
It's my pleasure to welcome all of you to this special occasion as we celebrate National Mathematics Day. This day dedicated to the memory of, as Murtuja was saying, great Indian mathematician Srinivasa Ramanujan. And it's a reminder of the profound impact that mathematics has on our world. Mathematics is not just a subject, but it's a way of thinking, a tool to understand the universe, and a language that connects us to the beauty of logic, patterns, and structures. It is, it influences every aspect of our lives, from engineering and technology to the art and music. Our university, SR University, is one of the leading institutions in India, known for its emphasis on research, innovation, and excellence in education. We take pride in nurturing, talent and providing our students with opportunities to excel in their chosen fields. At SR University, we are deeply committed to advancing mathematical knowledge and its applications. The Department of Mathematics at SR University is growing steadily, and we are excited about the opportunities ahead. We are having more than 20 doctoral faculty and more than 50 research scholars in our department. Our university is offering a full-time PhD program with a stipend of 40,000 rupees per month for motivated buddy researchers. Our department also offers MSc in Mathematics, MSc in Statistics, and we have further focused on launching, innovative programs such as MSc in Mathematics and Scientific Computing and BTech in Mathematics and Computing during the next academic year. We also actively engage in outreach programs, including FDPs, workshops, and conferences to foster a vibrant academic environment. And today, we are honored to have with us Professor Thangadurai sir from the prestigious Harish-Chandra Research Institute, Allahabad, as our esteemed speaker. Professor Thangadurai is a distinguished mathematician whose contributions to the field have been widely recognized. We are privileged to hear from him on this occasion, and I'm sure his insights will inspire all of us to delve deeper into the fascinating world of mathematics. Before we proceed, I would like to extend my heartfelt gratitude to our faculty, staff, in particular, Dr. Gulam Murtuja, who has arranged this particular program. And I encourage all participants to engage actively, ask questions, and make the most of this wonderful opportunity. Let's honor the legacy of Srinivasa Ramanujan by continuing, to explore, learn, and innovate in the field of mathematics. Thank you, and I wish you all a fruitful and enriching session. Thank you, sir.
Thank you.
Thank you, HOD sir, for those wonderful words. As you know, we gather today to celebrate Mathematics Day. So let us take a moment to revisit the inspiring journey of the legend Srinivasa Ramanujan. So we have a short video. So please turn your attention to the screen for the video presentation. So please allow me to share the screen, sir.
You can. Sir, you need to
someone mastering trigonometry by the age of 13, solving infinite series by the age of 14, and inventing new ways to solve higher order equations by the age of 15. All of this without any formal training in mathematics. That someone was none other than S. Ramanujan, the man who knew infinity. In his short life of just 32 years, Ramanujan changed the course of mathematics. But the man had his own share of struggle. Ramanujan was born in Madras, British India, to a very humble family. His father was a clerk in a shop, and his mother, a housewife who sang at a local temple. At an early age, Ramanujan showed signs of his mathematical genius, but he struggled a lot at other subjects, often failing in them. When he was 11 years old, he was gifted a book on trigonometry. Ramanujan mastered trigonometry in just 2 years. But the book that really changed his life was the one that contained 5,000 theorems, which he studied in detail. By 16, he was developing his own theorems. Back in 1900s, mathematics was not an option to make a living in India. He showed his work to many foreign mathematicians, but all of them said that Ramanujan was unconventional and lacked the formal education. But when his work came across the desk of G.H. Hardy in England, the latter could not believe his eyes. Hardy decided to call Ramanujan to England. Hardy, along with his colleague Littlewood, further examined Ramanujan's work, after which Littlewood said, I think we can compare him with the great German mathematician Jacobi. In England, Ramanujan made a great progress working with Hardy and Littlewood. Ramanujan was exceptionally good at infinite series. Before him, there was an infinite series for pi. The problem was that it was very slow. It took 600 terms to come to the value of 3.14. Ramanujan, on the other hand, developed a series that would converge to 3.141592 just after one term. After spending time with him, Littlewood told Hardy, forget Jacobi, we can compare him with Newton. Another famous incident that shows Ramanujan's genius was when Hardy once came to meet him. When he got there, he told Ramanujan that the cab's number 1729 was rather a dull one. Ramanujan said, no, it is a very interesting number. It is the smallest number expressible as a sum of two cubes in two different ways. 1 cube plus 12 cube and 9 cube plus 10 cube. This number is now known as the Hardy-Ramanujan number. The best incident that is noteworthy is when Hardy came up with a scale of mathematical ability that went from 0 to 100. He put himself at 25. David Hilbert, a great mathematician, was at 80. Ramanujan was at 100.
Thank you for the video watching. Now moving forward, it is my honor to introduce our distinguished speaker for today's event, Professor R. Thangadurai sir. So, Professor R. Thangadurai sir is a distinguished mathematician specializing in number theory. Professor completed his MSc in mathematics at St. John's College, Palayam Kottai in 1991. And further, he pursued an MA in development communication and Madurai at Madurai Kamaraj University. He embarked on a remarkable academic journey, starting as a junior research fellow at the Harish-Chandra Research Institute, Allahabad, progressing to a senior research fellow, and later serving in various esteemed positions, including postdoctoral fellow at the Institute of Mathematical Science, Chennai, and also visiting scientist at the Indian Statistical Institute, Kolkata. Currently, he is a professor at Harish-Chandra Research Institute, Allahabad. His PhD thesis title is Some Questions on of Arithmetical and Combinatorial Nature, and it was supervised by Professor Sukumar Das Adhikari. Professor Thangadurai has authored numerous research papers, books. Also, he has guided several PhD theses and project students, significantly advancing in the field of number theory. So thank you, sir, for accepting our invitation today. Now it's over to you, sir. You can start your talk, sir.
Okay. I'm thankful to the department and elaborate introduction. I will share my screen.
Sure, sir.
Yeah. One second. Okay, one second. It's not visible here. Okay, in this mode. One second. It's not visible here. It's supposed to be. One second. Full screen presentation. Yes. Is it visible? Hello?
No, sir.
Hello?
Yeah, now it's visible, sir. Okay, sir. Fine.
Okay. Full screen, no?
Yeah, fine, sir.
Yeah. Okay. So okay. So my title of the talk is Magic Squares and Elliptic Curves. Uh, okay. So this is Ramanujan. He classified magic square 5 by 5 magic square. In fact, parameterized. But we will stick to 3 by 3, which is simpler, but one problem is still open. I will connect to the current mathematics elliptic curves. Okay. So we will start with simple magic square 3 by 3. So 3 by 3 magic square is a array, 3 cross 3 array of integers, a11, a12, a13, etc. 9 integers. Each row magic, the square is magic. Whenever we say magic square, it means each row sum up to same number, each column also sum up to same number. Not only that, diagonal sum is also same, and counter diagonal also it's same. Okay, so then only then we say it is a magic square. Okay, so when the total sum of all the entries, if you see either 3 rows we are adding or 3 columns we are adding, therefore 3 times s, total is 3s. Instead of that, we add differently. If we add all the entries of the middle column, middle row, middle column, middle row, diagonal and counter diagonal. So in the middle column, middle row, counter diagonal, when we add all, so we will cover all the distinct 9 numbers plus 3 times a22 will come. Okay, the total sum is, because four rows kind of we are adding, therefore 4s total, but that same as 3s plus 3 times a22. This means the middle term a22 is nothing but s by 3. Suppose the magic square is total, I mean each row add up to s. If it comes, the middle row, middle term a22 must be s by 3. Okay, using this we can parameterize this. Okay, we put s by 3 equal to a. It means the middle term of the magic square is a. Then we choose any integer b and c such that this becomes a magic in some sense. So total now sum is 3a. If you see first row, a plus b plus, a minus b plus a plus b plus c plus a minus c. This is going to 3a everywhere. The diagonal also, counter diagonal also, everything add up to 3a will come. This is a kind of parameterization. You start with any abc, you plug values for abc, and you just put the values in this square, you will get a magic square. Okay, in this parameterization we can see that for instance, if some entries are repeating, it means, for instance, a plus b is same as a minus b if and only if b equal to 0. Okay, so it means some condition on abc will come. Okay, this is important. We will connect. We will use this in particular information later. So, thus, in a magic square, if we get a repeated entries, then this kind of condition on B and C has to happen. Okay. Now, given a 3 by 3 magic square, we parameterized it for any ABC. Okay, now we, by looking at this entries in the magic square in the parameterization, we arrive at something. Entries are in AP, arithmetic progression. For instance, you see, the I have reordered the terms, 9 terms, in this way: a minus b minus c, a minus b, a minus b plus c. This is a arithmetic progression with common difference c. Each row is 3-term arithmetic progression with common difference c, and each column, if you see, it's again 3-term arithmetic progression with common difference b. That's what each row terms are AP, and the common difference is C. Each column terms are AP in AP, and the common difference is B. Conversely, if we are given 3 such arithmetic progressions with rows are same common difference, columns are same common difference, then we can able to construct the magic square. Why? Because once we know, we just put it this way, and then correspondingly we form the 3 by 3 array, okay, which will form the magic square. Okay, so in order to construct a 3 by 3 magic square, it is enough to construct three 3-term AP with common difference C, okay, and the middle term also common difference some other thing, okay, some other. This is also in. Now the question is, can we construct 3 by 3 magic squares with each entry which is a perfect square of an integer? Okay, this is easy. You see 5 square, 1 square, 7 square, then you permute it. 7 square, 5 square, 1 square, 1 square, 7 square, 5 square. This is a clear cut magic square. The counter diagonal, everything add up to same number. Okay, so this also can be parameterized for any given pair of integer m and n. This will produce this kind of infinitely many magic squares of this kind. In 1970, Martin Gardner posed the following problem. What question he asked? Can we construct 3 by 3 magic square whose entries are distinct perfect square? Because you see, the whatever we constructed, many entries are repeated. So what he wanted, all 9 entries should be perfect square, all 9 entries should be distinct perfect square. So whether is it possible to construct or not? Okay, from the parameterization of 3 by 3 magic square, we have already seen if a term is kind of repeated, only one this kind of condition has to happen. Okay, the way we parameterized, from that this, if this condition happens, then it will be kind of entries are repeated. So we, while choosing, we have to choose such a way that this condition is not happening. Okay, first we look at the example. First 10 perfect squares: 1, 4, 9, 16, 25, 36, 49, etc. Among that, 1, 25, 49, this is in AP. This all with a common difference 24. Okay, in general, perfect. In general, you look at the three perfect squares: a square, b square, c square, which are in AP. What does this mean? It means consecutive difference should be same. Difference should be same. B square minus a square equal to c square minus b square. So this is same as saying a square plus c square equal to 2 times b square. This is what arithmetic progression means. 3-term arithmetic progression means. Since b is non-zero, this a square plus b square equal to 2b square, we can rewrite it as a by b whole square plus c by b whole square equal to 2. This, if you look at it, we the integers we want to in among squares, we want to create a arithmetic progression in length 3, which is equivalently saying this is a kind of known equation. You see, x square plus y square equal to 2. It is a circle. Okay, circle. Thus, finding three-term AP of squares in integers is essentially equivalent to finding rational points on the circle x square plus y square equal to 2. Here, any circle conic equation can be parameterized. So in this way, we can able to parameterize all the solution rational points on this circle also. So for instance, the points on this circle are described by this formula. When you take x to be any given integer m, you take x to be m square minus 2m minus 1 divided by m square plus 1, and the y to be this way. This will, given any, you choose any integer and plug this value for x and y, this will satisfy this will be on the circle. Okay, this is the parameterization of the circle x square plus y square equal to 2. So this way we can able to find all the squares which are forming arithmetic progression. But the point is, in this, what we have not taken care is the difference, common difference. We want to get three term AP of squares whose common difference is same. Okay, so here if you choose three different integer m, you may get three different AP in among squares, but the common difference may not be the same. Okay, that's the only trouble. So now again we will look at it. 1, 25, 49 are squares in AP with common difference 24. Again, one can check this three rational squares are also forming AP in rational number with common difference 24. Okay, so the question is, how many rational squares are there which form three-term AP with common difference 24? Or in general, for a given natural number d greater than or equal to 1 as a common difference, how many rational squares we can form as a three-term AP with the common difference d? Okay, general question. Okay, so we have a kind of bijection. So d is fixed, not a rational number, it is a integer. D is fixed, d is greater than or equal to 1 is a integer. Then the triple ABC is in bijection with tuple m comma n. Okay, what is ABC? ABC is nothing but a square, b square, c square, which is forms an arithmetic progression whose common difference is d. This triple is in bijection with m comma n. M comma n satisfies the equation d times n square equal to m cube minus m. Okay, so given that in bijection means what? Given a triple ABC, I should be able to find out m comma n such that m comma n satisfies this equation. So that's what given ABC means. I know the input of A, B, C values. From that ABC, I have to compute m and n. The formula is given. M is nothing but C minus B by A minus B. N is nothing but whatever is given. Similarly, this is one way. Similarly, given a pair m comma n satisfying the equation, we should be able to get three ABC whose square forms a three-term arithmetic progression with common difference d. That again formula is given explicitly. Okay, this is a computation. Okay, so this what it says, we are trying to transfer the problem of computing several three-term arithmetic progression of squares with the same common difference to different kind of solution set. Okay, this is what we are trying to transfer the problem to other. Why this, when we transfer some other way, that if that particular form is easy to compute, then we should be able to get back our ABC also. Okay, that is why we are trying to transfer. So the question now is, d, y square equal to x cube minus m. dy square equal to x cube minus m. We are looking for solutions, rational solutions, m and n. Okay. So in the when we put ABC equal to 157 means 1 square to 25 49. That is what our example is. So the m and n is minus 1 by 2 comma 1 by 8. That satisfies this particular equation. Okay. So using this result, we can get all tuples ABC of rational numbers whose squares are in AP with common difference D, using m and n, the solutions of this particular equation. Okay, now there is a, so we really want, we don't want, this is a kind of twist there. We want y square equal to x cube minus d square x, that type of equation we want. For that I am just doing some transformation, so that the previous theorem is indeed same as this theorem. So for a integer, yeah, a d, for a given integer d, the triple of rational numbers ABC whose squares are in AP with common difference d are in bijection with the rational solutions x comma y with y non-zero, satisfying the equation y square equal to x cube minus d square x. Okay. So in fact, the correspondence, the bijection is goes like this: ABC, the triple is going to tuple the pair with given input A, B, C, and D. Similarly, given x comma y satisfying this equation, we can get triple. Okay, same theorem I have translated into by just doing a transformation. I have changed the equation to this way. This is the kind of right form of elliptic curves. Okay, so we started with the question of existence of magic square whose all entries are perfect square and all distinct. Okay, whether such a magic square exists or not. Okay, so that is the question we are trying to address. Okay, so for that, first we since we know 3 by 3 magic square, we can parameterize. But once we parameterize, then we transform parameterized by three rational numbers A, B, C. This three rational numbers, this is in bijection with two kind of pair m comma n satisfying some other equation. So we have changed the problem into uh, this solutions, set of rational solutions of y square equal to x cube minus d square x. Okay, with y non-zero. Okay, now we define an integer, a positive integer n that occurs as a common difference of arithmetic progressions of three rational squares. Means this is what we have been seeing, three term AP we are looking at among squares whose common difference, suppose if it is n, then this n is called a congruent number. Okay, this is a term, just congruent number. So for instance, 24 is a congruent number. So just because this is the 24 is the common difference of the AP 1, 25, 49. 1, 25, 49 we can divide by 4. Then 1 by 4. 1 by 4 is a square of a rational number. 25 by 4 is a square of a rational number. 49 by 4 is a square of a rational number. Therefore, the 24 by 4, that is 6. 6 is a congruent number again. Is a common difference. Similarly, 7 is also a congruent number. 5 is also a congruent number. But 1 is not a congruent number, as there is no arithmetic progression of three rational squares whose common difference is 1. Equivalently saying, the equation y square equal to x cube minus x. Why I am looking at this equation? Because the d square is common difference d is 1. Therefore, I am taking x cube minus x. Y square equal to x cube minus x. This doesn't have a rational solution with y non-zero. That is the reason this 1 is not a congruent number. Similarly, one can prove that Among the first 10 natural numbers, 5, 6, 7 are the only congruent numbers. And in fact, it is an open problem. Is the answer is not yet no. Are there infinitely many congruent numbers do exist or not? Okay, it's an open problem. This is not solved yet. Okay, we look at the equation y square equal to x cube minus n square x. So the right hand side cubic polynomial I'm looking at, x cube minus n square x. This can be factorized into x minus n times x plus n. So this cubic has three distinct solutions, roots. Okay, so therefore the discriminant of this cubic is non-zero. Therefore, we say this equation, the solution set y square equal to x cube minus n square x, we call congruent number elliptic curve defined over Q. First, we will see what is elliptic curve means. An elliptic curve over Q is an equation in x and y of the form y square equal to f of x, where f of x is the just a cubic polynomial, x cube plus ax plus b, where a and b are fixed integers. Okay, and this cubic f of x has distinct roots, three distinct roots. Then only then we say this solution set is a elliptic curve. Okay, any point, any points on the curve, it means either x comma y, where x and y coming from a rational number. It means x, little x and y satisfies the equation, means this second coordinate y square, if I raise to the power 2, that is that value is same as x cube plus ax plus b. Okay, so either x comma y belongs to rational numbers satisfying the equation, or a point at infinity, something which is coming from geometry. Okay, so you take it as it's an identity kind of a point at infinity. The set of all points on the curve, we collect it in the set E of Q. This we are trying to give a group structure to this. In fact, by doing that, it becomes a abelian group. Okay, this is a geometric object. This is a set of solution set. E of Q is nothing but this set of all x comma y belongs to Q square, such that x and y satisfying some polynomial equation. Okay, this is a solution set along with the point at infinity. We want to give a group structure to this. So geometrically, first we will motivate how to give a group structure, then I will do the group operation. Okay, geometrically, you take 2 points on the curve, on the set. Okay, P and Q. P and Q, you take P and Q, I am taking from E of Q. What does this mean? It means P satisfies P equal to x1, y1, Q equal to x2, y2. X1, y1 satisfies the equation, x2, y2 satisfies the equation. Once it is satisfying the equation, I can in the plane, we can able to join the point P and Q. It means I am taking a line segment passing through P and Q. What does this mean? A line segment means y equal to mx plus c, where m is the slope of the line. Okay, this I plug y equal to mx plus c in the equation. In the equation is nothing but y square equal to x cube plus ax plus b. When I plug y, instead of y, I put mx plus b, mx plus c whole square equal to x cube plus ax plus b. Then it becomes a polynomial in degree 3. Already I have two solutions of this polynomial. What is that? So two solutions, the x coordinate of p and the x coordinate of q. They are solutions of this polynomial already. Okay, so therefore I can get, since the cubic degree, two solutions are already there, therefore inside q, therefore the third solution also will be there. Okay, so then once I get hold of the x part of that, then by plugging, suppose x3 is the coordinate I have got through this method. x3q plus ax plus b, whether this is a perfect square or not, I have to check. So once I check, then I can able to compute y3 also. Okay, so these are all just I'm telling geometrically, but everything can be made formula. This you see line joining 2 points. We know how to do line joining 2 points. The we have to find the slope and we have to plug the values. The okay. So therefore, I'm coming to the okay. Now we want to give a group structure. Okay, so for that I am trying to define addition. Addition means it's not the usual addition. This is elliptic curves group operation. The group operation. So first we take p1 and p2. P1 is nothing but x1 y1. P2 is nothing but x2 y2. P1 is not equal to p2, and p1 p2 are not identity. So once we have taken P1, P2, we can take the slope of the line joining P1, P2. The slope is nothing but it's given by, suppose x1 is not equal to x2, the slope is nothing but y2 minus y1 by x2 minus x1. If x1 equal to x2, that means it is not a it is a tangent. It is a tangent. So therefore we know the formula for the tangent, how to compute the slope. Okay, so once we compute m, then by plugging y equal to mx plus c, we plug it in the thing. We can find the x3. We can find the x3 value. The x3 value is nothing but m square minus x1 minus x2, and then by plugging x3, and we can find y3. Y3 is nothing but m times x1 minus x3 minus y1. Okay, one can get over q. So this is a kind of operation p1 plus p2. P1 plus p2 is a kind of binary operation I'm defining in EQ. This forms a group. One has to check closure property, then whether inverse exists. Identity is the point at infinity is the identity. Okay, so inverse is nothing but the reflection. Okay, so everything will come. Okay, so this is called this method is called chord tangent method. The line joining the points p1 p2 has a slope m given by the formula. The alternate second one is from the limiting case when chord becomes tangent at p1. So the equation of line is y equal to mx plus c. We plug the value of y in the cubic. So we have two roots of the cubic, which are the x coordinates of p1 p2. Then therefore we can able to get x3. Okay, so we could have defined okay, so when we plug x3 into the equation and we get y3, we okay, so here there is a twist in that tail. So the negative of this point here, it should be y3 prime, y3 x3 comma y3 prime. The negative is going to be the p plus 1. Okay, p1 plus p2, which is equal to p3. Okay, y3 is nothing but the negative of y3 prime. If we define this itself x3, this is y3, if we define, then it will not satisfy the group law. Okay, that's the only trouble. So in the pictorially if you see, p and q line joining will intersect the curve one more point. That point is p star q. P star q we cannot define to be p plus q. If we define p plus q, that is p star q, the third point, then the group law will not be satisfied. We take the reflection. Why it is a reflection? Our equation is y square equal to x cube plus ax plus b. Therefore it is symmetric with respect to x-axis. Therefore we can take the reflection of this point. That is nothing but if it is y3 prime, that is minus y3 prime. Minus y3 prime is the y3 we are taking. Okay, so this way we can able to, and you see it's by looking at the geometric group law, this is either whether I is joining p to q or q to p, the line joining is one and the same. Therefore abelian group, this is a clear cut abelian group. So what we have done, we have collected the solution set of y square equal to x cube plus ax plus b. In our case, x cube minus d n square x. This is the elliptic curve we have taken, and we have collected all the rational points, and this becomes a abelian group. Okay, by structure theorem, the abelian group. So of course, model Whale, what they proved is it is not only abelian group, it is finitely generated abelian group. So it is a finite generator will be there, in the sense, if I know only finitely many elements of this particular group, then I can able to generate all the elements of the group. Okay, that's not a finitely generated abelian group. By the structure theorem of finitely generated abelian group, this is isomorphic to a torsion part and free part. It's a direct sum of torsion part and free part. Torsion part is nothing but the finite group sitting inside E of K, E of Q in our case, and the free part is the infinite part. Infinite part is isomorphic to Z power R. Okay, for some R greater than or equal to 0. It sometime it can be R can be 0 also. Okay, only finite group it become. Finite group also finitely generated. Therefore, there is no contradiction. So R can be greater than or equal to 0. So we have what we have done. We started with we wanted to construct three-term arithmetic progression among squares with the same common difference. Okay, for three many. That problem we converted into elliptic curve problem in the rational points. Okay, that's what so far we have done. Okay, we say for a natural number n, the en is nothing but y square equal to x cube minus n square x is called congruent number elliptic curve. By the above discussion, en q, the set of rational points on en, forms a finitely generated abelian group, and hence en q is isomorphic to a finite part direct sum free part. Okay, where r is the rank of the elliptic curve. The finite part is well understood. This is well understood just because this is nothing. This is a subgroup of E and Q. The points are only 4 points will be there. This is a cardinality is 4, and 0 is element of, because you see, when we take x equal to 0, y equal to 0, this is satisfies the equation. It's a Therefore 0 is a point of the curve. N comma 0 is also point of the curve, minus n comma 0 is also point of the curve. These are the only finite order points of this elliptic curve. Okay, and along with the identity. Okay, so you see in this, I just recall, because this is the crucial point we need. In this bijective correspondence, when we transformed our arithmetic progression among squares to elliptic curve point, rational point, with y non-zero. Okay, y, the second coordinate should be non-zero. That is what the correspondence says. So therefore, but we looked at the finite part of the elliptic curve group. Finite part is nothing but just y is 0 along with identity. Okay, therefore what we can conclude, if a natural number n is a common difference of three-term arithmetic progressions of rational squares, then one three-term arithmetic progression, if it is there, then we have infinitely many arithmetic progression. Why this is true? Because once I have a three-term arithmetic progression whose common difference is n among squares, rational squares, then y term is non-zero according to the previous correspondence. Y term is non-zero means that that particular point, x comma y, will not lie inside this finite group. Okay, it has to lie in the bigger group, that is nothing but the infinite part. Once one point is there, then I can add that which is of infinite order. Therefore, suppose p is there inside, then p plus p I can compute. That is also not finite order. Therefore, this is an infinite order, p plus p, 2p, 4p, 6, 8p, etc. I can continue. These are all different. It cannot be same. Okay, so therefore, one term arithmetic progression, if I can construct with a common difference n, then I have plenty of arithmetic progression among squares whose common difference is n. This is what the algebraic part. When we change the problem, we could draw the information because of this algebraic setup. Okay, the structure theorem of finitely generated abelian groups. Okay, so I have given a proof. Proof is same. We have seen that three-term AP of rational squares with common difference n leads to a rational point on En, and such a point has infinite order by the above assertion, because the y is second coordinate has to be non-zero. That means that point will not be inside T. That means it will be inside the other part. Other part means infinite part. Okay, therefore by repeatedly adding the point to itself on E and Q gives the infinitely many rational points on the curve, which leads back to a new three-term AP of rational squares with common difference n. Okay. Now we get back to our magic squares of squares. If a square, b square, c square form a three-term AP, then by taking capital X to be a plus c by 2, capital Y to be c minus a by 2, and capital Z to be b, we can get Pythagorean triple. X square plus y square equal to z square. Conversely, every Pythagorean triple x comma y comma z generates a three-term AP of squares by taking a to be x minus y, b to be z, and c to be x plus y. Okay. Now, what is the observation? Suppose we have two arithmetic progression of squares of length 3 having same common difference of terms. Okay. This is correspond. So each arithmetic progression corresponds to one Pythagorean triple. So now we have two arithmetic progression of length 3. Therefore, that we will have two different Pythagorean triples. So each Pythagorean triple will determine the Pythagorean right angle triangle, and the common difference becomes in the right angle triangle area is going to be same. That's what the observation is. The common difference of these two arithmetic progression of squares of length 3 is same as the area of the Pythagorean corresponding Pythagorean right angle triangle. Okay, how it is? Suppose a1 square, b1 square, c1 square, and a2 square, b2 square, c2 square are the two arithmetical progressions of length 3 having common difference, same common difference. The corresponding Pythagorean triples are xi, yi, zi, respectively, I equal to 1 to 2. Now, from the what is the correspondence? Once you assume the first part, then once ai, bi, ci is given, then I can construct xi is nothing but ai plus ci by 2, yi, etc. Using this, since common difference is same, it means b1 square minus a1 square equal to c1 square minus b1 square. This common difference is same as the second common difference also. Therefore, b2 square minus a2 square, which is same as c2 square minus b2 square. This information tells you that just we have to say that the corresponding Pythagorean right angle triangle area is same. That means we have to compute the formula x1 y1 by 2, which is same as x2 y2 by 2. We just compute x1 y1. X1 already we know what is that in terms of a and a b, a b c, and y1 also we know. Just we plug and we use the common difference, that we get x2 y2. Okay, this is just easy computation. So conversely, if we have this two right angle triangle, Pythagorean triple right angle triangle, and having same common the area, okay, that will lead to the common difference. Okay, two arithmetic progressions. Okay, so this what it says, if n is a common difference of three term arithmetic progression of squares, a square, b square, c square, then the area of the right angle triangle formed by the corresponding Pythagorean triple xyz, which is coming out to be n by 4. If we start with n, common difference n by 4 we are getting. Okay, so any integer, positive integer n bigger than 1, we can always write as square part and square free part. That is, n can be written as s square times r, where r is a square free part. Suppose I have a Pythagorean triple xyz, whose Pythagorean triple xyz such that the Pythagorean right angle triangle area is nothing but r, suppose the square free part of the n. Then by multiplying the square part s with the Pythagorean triple sx, sy, sz. This is also a Pythagorean triple whose area is s square times r, which is nothing but given n. Therefore, we can always assume n to be square free integer. If we can do for square free integer, we can do for every integer. So that's what this reduction is. So we link the above observation with a congruent number as follows. Okay. Let n be a square free positive integer. Let x, capital X, Y, Z and small x be rational numbers. The capital X less than capital Y less than capital Z. Then there is a one-to-one correspondence between the right angle triangles with legs x, y, hypotenuse h and area n. Okay, you collect all those x comma y comma z, which is right angle triangle with legs x and y, hypotenuse z and the area is n. This is corresponding with x, the given little x, such that x minus n, x plus n, these are all perfect squares of a rational number. Okay, so once you are given a okay, so why this is nothing but observation only. Why it is? Let us see this correspondence, how we are giving. Given a x, y, z, we want to compute little x. Little x, you take it to be z square by 4. If you are given little x, then which is a square of a rational number. Okay, little x is a square of a rational number. Therefore, you take x to be square root of x plus n minus square root of x minus n and y to be etc. This way, this is the correspondence. In particular, if n is a congruent number, then the right angle triangle, we will get one right angle triangle whose area is n. Okay, that means there exists little x. Given a congruent number, we get a little x, which is a rational number, perfect square of a rational number. Not only x, x minus n, x plus n, both all are squares of a rational numbers. That is what this correspondence says. Okay, these are all elementary observations which you can find it in Koblitz book. I will give you the reference later at the end. Okay, I guess I have given kind of some sort of, I am trying to deduce something more. Okay, using this calculation, what we can say. Okay, let me see. Okay, if x, y, z are the sides of the right angle triangle with area n, then we have x square plus y square equal to z square and xy divided by 2, which is nothing but little n. This is what the area is n, and it is a Pythagorean triple. Okay, therefore x plus or minus y whole square, this is same as z square plus or minus 4n. This is nothing but, because of Pythagorean triple, this x plus or minus y whole square, we can rewrite it as x square plus y square plus or minus 2n, we will write. Okay, so that is same as z square plus or minus 2n xy, no, xy 2xy we will have, that is nothing but 2xy means 4n, this is plus or minus 4n. So therefore you see z by 2 is nothing but z by 2 whole square is nothing but x plus or minus n is a perfect square. That's what we are getting. If we start with the right hand x, y, z are the sides of the right angle triangle with area n, then we get little x. Little x is nothing but z by 2 whole square. Not only little x is a perfect square, but also little x plus or minus n is also perfect square. This is it. Okay. So by multiplying these two together, we can derive, okay, one more same solution only. We are trying to get the elliptic curve equation. Okay, just by doing the transformation from this calculation, what we can get, we have a pair. We start with the rational X, capital Y, capital Z, sides of the right angle triangle with area n, then which leads to a point x comma y, little x comma y, a rational number x comma y, satisfying the cubic equation y square equal to x cube minus n square x. Okay. The previously we have seen the same thing with the three-term arithmetic progression. Now we transform the problem again to right angle triangle, and we do the same. I mean, it is just same. Thus, given a right angle triangle with a rational side x, capital X, Y, Z, and area n, we obtain a point little x comma y in the xy plane having rational coordinates lying on the curve. Conversely, what about the converse? Converse in the sense, given a point x comma y with x and y are rationals and lie on this curve y square equal to x cube minus n square x. Okay, whether this from this x comma y can be construct capital X y z such that this is forms a legs of the triangle and hypotenuse such that the area is n, whether the converse is true or not. Now we look back our thing. You see, x is nothing but z square by 4. Okay, z is nothing but 2 times square root of x. When we take square root of x, we always take a positive square root only. Therefore, z is a rational number, which is a positive rational number. Okay, z is a positive rational number. Therefore, x is nothing but the positive rational number square. When we take x comma y belongs to this cube such that it lies on the curve, we cannot make sure that x is a positive rational number square. It can be negative. Okay, that the problem is there. And not only that, the x has a divisibility. You see, x denominator of x is nothing but divisible by 2. Okay, so therefore general perfect square in the rational number will not lead to the converse. So these are the two hurdles. The coordinate x coordinate is positive rational square, and the denominator of x coordinate is divisible by 2. For the converse, we need to work with a smaller subset. Let x comma y be a point with the rational coordinates on the curve y square equal to x cube minus n square x. Suppose x satisfies the following two conditions. It is a square of a rational number, positive, and its denominator is even. Then there exists a right angle triangle with rational sides and area n, which corresponds to x under the correspondence, the what we have talked before. That means we have to restrict to ourselves in this set. X comma y belongs to q cross q such that x comma y satisfies this equation. X is nothing but positive rational square, and 2 divides the denominator. This set, instead of working in this set, we can work in a subgroup, because E and Q is a group, abelian group. We can look at subgroup. If the subgroup and this set is kind of same, then we are done for it. Okay, so we look at 2 times E and Q. This is a subgroup. What is 2 times E and Q? It's a symbol only. Set of all elements P inside E and Q such that the P is written as Q plus Q. Okay, this is addition. This addition is elliptic curves addition. Okay, this forms a group. This one can check, it's a subgroup. Okay, and this subgroup minus the identity element has no finite order point. Okay, this is also a fact from the elliptic curve side. Now, we see that for take any point P belongs to this particular subgroup. That means there exists Q, which is inside E and Q, which is comma x comma y. Q is nothing but x comma y, such that P can be written as P is obtained from Q this way, Q plus Q, by adding Q to itself. Okay, so adding in the sense of elliptic curves addition. So this elliptic curves addition, the formula tells you that the x coordinate of P will look like x square plus n square divided by 2y whole square. Okay, so the x coordinate of P is a perfect square and the denominator of x coordinate divides 2. Okay, denominator divides 2. Therefore, we have the following characterization for this subgroup. What is this subgroup? The 2E and Q. So suppose you take any point P, which is nothing but x naught y naught, which is inside E and Q minus the identity, and this particular point belongs to the subgroup if and only if what happens, the x coordinate and the x coordinate minus n, x coordinate plus n, all are perfect squares of a rational numbers. This particular theorem proof is using valuation theory, little bit of some more, I mean, valuation theory or periodic kind of valuations. One has to know this. You can check it in this elliptic curves and cryptography book by Washington. Okay, so this is what really you see. If any point in this subgroup which is not an identity point, then the x coordinate forms an arithmetic progression with common difference n. This is what, and it is a perfect square of a rational number. This is what really we are looking for. Okay, this is the subgroup really we are looking for. Okay, from the observation 3 and observation 1, what we have, there is a one-to-one correspondence between right angle triangle with rational sides x, y, z and area n and the pair x, comma plus minus y inside the subgroup minus identity. Then this is the correspondence. This x comma y comma z, that goes to x comma plus or minus y in the subgroup minus identity, and vice versa. How this correspondence is given by this formula. Okay, so we started with a magic square existence. Magic square, all the terms, whether distinct perfect square can be there or not. We transform the problem into by the parameterization of the 3 by 3 magic square. We wanted to construct 3 arithmetic progressions of same common difference. Okay, so that problem we transform to elliptic curves problem. Okay, therefore the existence of 3 by 3 magic square with the distinct, all entries are distinct perfect squares becomes this way. Prove or disprove, there exist 3 rational points, not integral points, rational points P1, P2, P3 in the subgroup 2ENQ minus identity for some integer n. Okay, for some integer n such that the x coordinates are in arithmetic progression. Why? Once one P1 is inside this, then the x coordinate of P1 and x coordinate of P1 minus n, x coordinate of P1 plus n, all are in arithmetic progression, all are perfect squares. So we will get 3 arithmetic progression in squares of same length, the same common difference, and the middle term, the x coordinates, also in arithmetic progression. That means this is the first we started with observation. This is the observation. You see, each row term is arithmetic progression and with common difference c. Each column, so if one one column is having same common difference, then everything will be same common difference. Okay. So therefore, this is what we are trying to construct, but among perfect squares, all are distinct. Okay. So this, the Martiner problem now becomes elliptic curves problem, the theory from the theory. Okay. Existence of 3 points, rational points on the subgroup 2 times En minus identity for some n such that their x coordinates are in arithmetic progression. Okay. Thus, the study of congruent number elliptic curve is linked with magic's squares of squares. Okay. In 2000, what are all known result? In 2000, Andrew Brumner, Silverman, and Zakanis, Xenakias, what they proved, any given n square free integer, they looked at this congruent number elliptic curve. Suppose gamma is a subgroup of rank 1, then gamma will never contain arithmetic progressions, non-trivial arithmetic progressions. Therefore, if we want to prove uh, the Martin Gardner's problem, we have to look for subgroup of rank 2, at least 2. Okay. In 1997, one person Salos, he come up with the example which is failed to be magic. It's a square of three distinct, I mean 9 distinct entries, perfect squares, distinct entries also, but failed to be magic only in the counter diagonal. Rest all it is magic. Unfortunately, only one place it was missing. Andrew Brumner, after this example, Andrew Brumner could parameterize this such an examples also. Okay, in 2019, one thesis, what he studied. So already we have seen Martin's problem. If we want to tackle, we need at least look at the rank subgroup of rank 2 at least. Okay, so En is the congruent number elliptic curve of rank 2, suppose. Then suppose if it admits some arithmetic progressions in x coordinates in d many, the d has to be at most 13 only. Okay. But if d is at least 3, then we are done. But here is at most only he could prove, some with some conditions also. So therefore, this problem is still open. One doesn't know whether such a magic square do exist or not. So the main reference of this talk is a paper of Robertson and a nice article of Conrad, which is on arithmetic progressions of 3 squares. For elliptic curves, one can give reference to Goblitz or Silverman first book or Washington. All 3 books are good reference for basic elliptic curves. Okay. The reference is this. So main reference I took is Robertson, Magic Squares of Squares, Math Magazine, 1996. And then this Kate Conrad, Arithmetic Progression, which is freely available article. The rest all just papers. With that, I will end my talk.
Thank you very much, sir, for this enriching talk. So I extend my heartfelt gratitude to the esteemed speaker, Professor Thangadurai, sir, for this excellent talk on magic squares and elliptic curves. Sir, your insights have not only deepened our understanding of these fascinating topics, but also have highlighted the beauty and elegance of this mathematics. So thank you, sir, for your time and expertise and to be with us today, sir.
Thank you.
Also, I would like to thank to our HOD, Dr. G. Ravikran, sir, for his guidance and support to organize this event. Also, a big thank to all the participants, faculty members, and students for their enthusiastic presence. Thank you, sir.
In case if somebody needed, you can share this.
Yeah, definitely,
my
sir.
talk.
Definitely, sir. You
Yeah.
already said to me. Now, also, sir, in future, if there is any possibility, we are delighted to welcome you in our SR University in person. We are
Sure.
honored to have you here, sir. We will be
Yeah.
host you. Please let us know if in future if you have any free time, any.
Okay.
So we will arrange all these things, sir.
Okay.
We are
Thank you.
delighted to host you, sir.
Yes. Thanks a
So
lot.
any concluding remarks for our HOD, sir?
Yeah.
Nothing, sir. If anybody have any questions, actually we can take.
Yeah.
There are few people.
Not in the chat.
Yes, sir. That was really a wonderful lecture. In fact, I have studied number theory long ago when I was doing my PG program, but I
Okay.
was not practicing that. So
Okay.
I'm just recollecting all those Fermat's last statements, last theorem and all again. And definitely, sir, this will be again a what you call turning point to my kind of research.
Okay.
So definitely we'll also take this in a different turn. And somebody is asking about an example for magic square, sir.
The example is the question, no?
Yes, sir, exactly.
Yeah.
So
Whether
finding
exists.
that itself. Yes, sir.
Yeah.
Thank you very much, sir. As Dr. Murtuja was saying, definitely we'll invite you again for our institution. We are also in a plan to conduct a workshop, sir. We require your guidance in, designing this BTech mathematics and computing course structure.
Okay.
So definitely, sir, we'll also invite you. We'll get in touch with you, sir, immediately in a few days.
Okay, sir.
Right, sir. Thank you very much, sir.
Thank you. Thank you. Bye.
Thank you, sir.
Thank you, sir. Bye.
Thank you, sir.
Murtuja, they are asking this
certificates.
No feedback. So shall we share them to their mails?
Yeah, we'll share.
Okay. So participants, you'll get feedback link to your mails. You can just click them and get the certificate.
Okay, sir. Thank you.
Thank you all for joining the meeting. So I'm concluding this.